Alrighty, so this little video, for those that are away on tournament week this week and need to know this, is a video walking through a buffer calculation. So this is a pretty typical buffer calculation. It's probably not the easiest one and not the hardest one, so right in the middle there. So we have to calculate the mass of this thing here. Now, as soon as I see this thing here, I must be able to identify that as an acidic salt. And in identifying it as an acidic salt, I know that this will fully dissociate and it will end up making these ions, and this ion here is a weak acid. So I'm going to ignore that until I come to the mass calculation. So again, calculate the mass of this thing here. That must be added to 200 mils. So here's my volume. And of course, that is going to be 0.2 litres. So 200 divided by 1,000 of 0.05 moles per litre ammonia. So here I've got my weak acid and my base conjugate pair that I can then, that will make my buffer solution. So this is going to give a buffer solution, and the buffer solution has to have a pH of 8.75. This is always just put in there as a disclaimer because we're going to add a mass of something to a volume, which will change the volume slightly, but for our purposes, we're going to not take into account that volume. We've got a molar mass given. This is pretty standard, and this is always helpful. If you get a Ka for something, that tells you, one, that it's part of the calculation, and two, that it's a weak acid. You don't get Kas for strong acids, and you don't get As for bases. Right, so that's a couple of good little tricks to help you along your way. So the first thing we're going to do is actually write a Ka expression for the weak acid part of the buffer, because we know that when we write a Ka expression, we get a mathematical representation that involves the weak acid and its conjugate base and the relationship between them. So that's our Ka expression. Now, the biggest difference that we're going to have in this situation is that we're not going to have any assumptions. So actually, when we're doing this calculation, we're adding NH4 plus ions from this source, and our NH3 is coming from a different source. So the only time we can make these assumptions is when we've just dissolved one thing, when we've just got a weak base or a weak acid. We haven't got two different sources. So I'm going to have four numbers to deal with. My Ka I can sub in straight away, 5.75 times 10 to the minus 10. I've got a pH, so I can 10 to the negative pH to give me the H3O plus. So I'm going to sub that in here. And then I've got a concentration of NH3. So I'm going to put that in there, which is 0.05. And I do not know the concentration of NH4 plus. So that's going to be my X. Right, so I'm just going to rearrange, and I'm just going to do all this on my calculator. So I'm actually going to multiply that X up and divide the Ka down. So X is going to equal 0.05 times 10 to the power of negative 8.75 divided by 5.75 times 10 to the minus 10. Right, so since I'm not that flash, you're just going to have to sit here while I do that. Okay, so shift log negative 8.75, so that's 1.77 times 10 to the minus 9 multiplied by 0.05 and divided by 5.75 times 10 to the power of negative 10. So my X is going to be 0.1546 moles per litre, and that of course is my concentration of NH4 plus. Right, so that's a good first step. Now I need to work out the rest of it. So I've got that many moles per litre of NH4 plus, but I'm going to make a volume of 0.2 litres.